Based on my initial tests, I already knew that the 5-amp PowerShield can provide lots of power even over extended periods of time. But since I recently changed the design to use individual chips instead of the IBT2 board, I thought it was a good idea to show you the new board and then do a load test to find out how it performs. Welcome to the IoTT channel. I am Hans Tanner. A special welcome to all new subscribers and welcome back to everyone else. I'm happy to see you back here. Starting this week, I shipped the new version of the 5-amp PowerShield based on the BTS7960 H-bridge driver chip. The revised board uses the same circuitry, but instead of using a pre-manufactured IBT2 board, I am now mounting the BTS7960 field effect transistors and the driver chip directly on the board. The advantage of the design change is a height reduction of the entire board by almost 4 mm, which makes stacking of several PowerShields easier. Furthermore, it allows for mounting more parts by the robot, so the manual assembly time is reduced and the build quality is more consistent. Once in a while, I read or hear concerns regarding using a chip that is no longer manufactured, which indeed is the case for the BTS7960. That, of course, is a valid concern, and I have 4 reasons why I keep using the chip for the time being. First and foremost, there is no technical reason for using a different chip. All important characteristics of the BTS7960 are right where they need to be. So far, the chips are readily available in quantities, and there is no indication that supply is running out anytime soon. It rather looks like the overall demand is slowing, and some dealers worry if they will be able to sell off their inventories and therefore are ready to give some discounts. If sourcing should become difficult, I have already identified the chip from current production I will use to replace it. The potential replacement has similar dimensions, so the changes to the PowerShield board will be minimal. And the price of the chip is low. I currently buy them for about 90 cents per piece in quantities of 100. Double that and the cost of a full H-bridge is less than $2. Now compare this, for example, to a DRV8874 chip, which runs in the neighborhood of $2.50 in quantities of 100 and does by far not perform to the same level in an application like the PowerShield. With that said, here are some pictures of the new revision PowerShield board. Same electrical characteristics, but reduced complexity compared to the old version. So let's hook it up and see how it performs under a heavy current load. For this test, I bought a set of 1 ohm 100 watt power resistors, and I connect 2 of them in series to the DCC output of the PowerShield. To run 5 amps through them in theory, I need to apply a track power of 10 volts, and the resulting power consumption of the resistors will be around 50 watts. That much power generates a good amount of heat, so I mounted the resistors on some brackets to make sure the heat can radiate away without causing any harm to the surroundings. For this test, I'm using my 5-amp lab power supply, and as it turns out, for true 5 amps, I had to set the voltage to about 15 or 16 volts. When measuring the resistance, my cheap 1 ohm resistors from Amazon in reality were more like 1.4 or 1.5 ohms, even when cold, and of course as they heat up during the test, the resistance is slightly increasing. But it looks the setting is working. I can test running 5 amps consistently over an extended period of time. The second current I wanted to test is 8 amps, as I consider that a very meaningful current output for G-scale layouts. To run this test, I used a 12 volt 30 amp DC supply I had laying around and built a second bank of power resistors. When the two banks are connected in parallel to 12 volts, they will consume slightly above 8 amps, and as things heat up, the current will be reduced to about 7.8 amps, which still results in a power consumption of about 90 watts, and I considered it good enough for the purpose of this test. Most importantly, also here I am able to run a test over an extended period of time to see how the PowerShield behaves under significant load. So by now you may ask yourself, why doing this test? Why is it important? Well, when it comes to model railroad power, track current is key. Each locomotive consumes a little bit of current, and the sum of all consumptions makes up the current that needs to be provided by the booster or H-bridge. And it is also this current that heats up the H-bridge, and by how much? That's what I wanted to find out. The reason for the heat buildup is the value of the resistance when the transistor of the H-bridge is conducting. There is an excellent paper from Texas Instruments that explains in detail everything that contributes to this power dissipation, but two factors are dominant. If we look at the transistor level, there are two phases that are relevant. First, the phase when the transistor is conducting. When running a DC signal, this is the case roughly 50% of the time, and it comes in short pulses of either about 60 or 100 to 110 microseconds. During this time, the power dissipation is the square of the current multiplied by RDS on. R is the symbol for resistance, DS stands for drain source and means the two legs of the transistor the current flows through, and on means the resistance during the on state of the transistor. The second important contributor is the transition phase, so when the transistor switches from on to off and vice versa. The power dissipation in this phase is not only a function of the current, but also depends on the track voltage. The general rules are the higher the voltage, the more heat, and the shorter the transition period, the less heat buildup. And if you want to learn about the details of this really interesting transition phase, consider studying the TI paper I mentioned before. The current is given by the application, so what really is important to avoid a lot of heat is the value of the resistance, and that we can look up in the datasheet of the H-bridge that is used. In a real full H-bridge application like a DCC booster, there are always two transistors conducting, one on the positive and one on the negative side. In the datasheet we find indeed two values, RDS on for the high side and for the low side. They can, but do not have to, be identical. It depends on the device. For the BTS 7960 we find typical values at 25 degrees Celsius of 7 and 9 milliohms. That is extraordinarily low and in fact is one of the main reasons for me to choose this chip. When running 5 amps, the resulting power dissipation is 25 times 0.016 ohms, which is 0.4 watts in total for both chips. Here is a table of values for some other chips. The DRV8313 I am using on the Red Hat for the low power DCC signal of the Loconet outlets has an RDS on of 240 milliohms, which at 5 amps would result in a power dissipation of 12 watts. Way too much. The DRV8874 used in a new MotorShield application comes with an RDS on of 100 milliohms, resulting in a 5 amps power dissipation of 5 watts. Not something that is sustainable for minutes. In general, these highly integrated and small footprint full bridge driver chips have a significantly higher on resistance than the high current chips like the BTS 7960. And that is why, in my opinion, a good booster should be built based on one of these high power chips. Even those will heat up considerably under significant load, as we will see in just a minute. Now, for my test, All I do is connecting the resistor to the track output of the PowerShield and turn the track power on. As a result, the chip is loaded with 5 or 8 amps and a duty cycle of 100%, which is the worst case the board will ever see when running a DCC layout. In fact, it never will see that really, because the locomotive decoders are pulsing the motor, which results in potentially high but very time-limited current pulses. If pulses from several decoders overlap, chances are high that the sum of overlaid brief pulses will trigger the current limit protection, even though the power dissipation over the entire cycle is way slower than what would be acceptable as total load. As soon as the track power is on, the power resistors as well as the BTS7960 chips of the PowerShield will start warming up. On the resistors, of course, that is desirable as it represents the energy used for running the trains. The PowerShield circuitry, on the other hand, I would like to see staying cool, but as we are burning 200 milliwatts on each chip, this is not going to happen. In fact, the chips will warm up considerably, but what I want to know is how much. The chip has an internal overtemperature protection which triggers at about 175 degrees Celsius. Of course, I hope we are not going to see such high temperatures, as this would be a range that comes close to where components could start desoldering from the board. So let's do the 5 amp test. I hook up the power supply to the PowerShield board and connect 2 resistors in series to it. Unfortunately, I do not have an infrared camera, so I measure the temperature the old-fashioned way using a thermometer. I have a 2-channel thermometer with thermocouples, so I place the sensor for channel 1 between the BTS7960 chips and the sensor for channel B on the power resistors. I then set the LED power supply to a fixed output current of 5 amps and let it automatically regulate the voltage. It starts at 15.4 volts, and with increasing temperature of the resistor, the voltage needed to push 5 amps goes up to about 16.5 volts. I then measure the temperature every 30 seconds, and here is the resulting curve. As you see, the start value is 30 degrees Celsius or 86 Fahrenheit, and that is due to the fact that I do this test in my attic. Of course, this adds to the worst case situation. But on the other hand, I'm probably not the only person who has the layout in a room that warms up in summer. On the other hand, I have the ceiling fans on, which leads to a nice air convection in the room, but no direct airflow down to the PowerShield or the load resistors. The blue T1 curve shows the temperature of the PowerShield chips, and the red T2 curve has the temperature of the load resistors. Once the power is on, both BTS7960 chips together dissipate about 0.4 watts, and consequently the temperature is rising. This goes relatively fast as long as the chips are cool and slows down when the temperature gets higher, and the increased temperature difference between chip and environment leads to more radiation and convection losses. And once the amount of power that is sent to the environment is the same as the power that goes into the chip, the temperature is stable. For 5 amps we reach a nearly stable temperature after about 6 minutes of operation, and the resulting temperature is around 80 degrees Celsius or 176 Fahrenheit. That sounds pretty hot and is definitely more than what you want to touch with your fingers. But it is not a problem for the chips or the board, and it is way below the overtemperature shutdown threshold of 175 degrees Celsius or about 350 Fahrenheit. Based on this test, I would recommend following setup for a train layout. Use a DC power supply with a nominal output current of 6 amps or more to supply the PowerShield. Connect the PowerShield and protect it with a 5 amp slow blow fuse. This gives protection against overload but allows for brief high current pulses from decoders. Set up the trip current of DCCX to 6000 or 6500 milliamps. This gives an absolute current protection at the set value and leaves some room for short-term pulses above the nominal 5 amp supply current. That, by the way, is another clear advantage of using a high-power chip. Thanks to the short-term peak current of up to 43 amps, it is possible to distinguish between general overload protection provided by the 5 amp slow-blow fuse and the peak value over current protection set by the trip limit of DCCX. When using an integrated driver with say 6 or 7 amps maximum current, such a concept is not possible, as you cannot allow the current going higher than the rating of the chip, not even for just a brief moment. This limits the tolerance of the system for short pulses, which are common at low decoder speed settings. Next, I changed my setup for the 8 amp test. I replaced the lab power supply by a 30 amp 12 volt supply I bought a few years ago to power LED strings. And on the load side, I added a second resistor bank with the same 1 ohm resistors with a true value of around 1.5 ohms. So the resulting current is 12 volts divided by 1.5 ohms, which is exactly 8 amps. When measured on the hot resistors, my final current was 7.6 amps, close enough. As before, I switched on the track power and started recording the temperatures of the BTS7960 chips, as well as on the load resistors. Here are the resulting temperature curves. This time the temperature of the load resistors is lower, as there now are 4 resistors to share the load, and the current in each is reduced by about 25% proportional to the voltage reduction from 16 volts to 12 volts. The temperature curve of the BTS7960 chips, on the other hand, rises faster as there is 3 more amps flowing through them. The total power dissipation of the 2 chips raises from 0.4 watts to slightly more than 1 watt, which is considerable. Consequently, the chips heat up faster and the end temperature is higher, somewhere around 105 degrees Celsius or 220 Fahrenheit, which still is significantly below the overtemperature protection trigger point of 175 degrees. So, given the fact that the real layout never leads to a 100% load factor or duty cycle as used for this test, setting the PowerShield up for 8 amps track current is not a problem at all. Depending on the number of G-scale locomotives you are running, it might warm up, but it cannot heat up to the point where damage is caused either to the board or to the BTS7960 chips. And if you plan to do that, here are my recommended settings. Use a DC power supply with a nominal current of 10 amps or more to supply the PowerShield. Connect the PowerShield and protect it with an 8 amp slow blow fuse. This gives protection against overload but allows for brief high current pulses from decoders. Set the trip current of DCCX to 8000 or 8500 milliamps. This gives an absolute current protection of the set value and leaves some room for short-term pulses above the nominal 8 amp supply current. Now, do not set the trip current of DCCX higher than 9000 milliamps. The current sensor input is protected by a Zener diode, and trip values higher than 9000 will not read correctly in DCCX, which means the trip current shutdown would not work as intended. And that's it for this video. I hope this information was useful or at least interesting for you, and you have a better understanding how track current is related to the temperature of your command station or booster. If so, please click the like button below to let me know, or let others know about your experiences in the comment section of this video. And if you are interested in this kind of content, do not forget to subscribe to the IoTT channel and click the bell icon, so you will always be among the first to know when a new video hits the tube. Thanks for watching and see you in the next video.